Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and we are on day 14 of our hashtag 30 Days of Code Challenge with Educative, and today's question is a fun one. Binary tree, zigzag level order traversal. Wow, let's get into this one.
Today, we are making the zigzag level order traversal simple, visual, and intuitive. If you've ever read a tree left to right and then thought, wait, what if the next line flipped directions? That's exactly what this problem is asking you to do. This is one of those problems that sounds complicated but becomes surprisingly straightforward once you understand the pattern. We're given the root of a binary tree, and we need to traverse it level by level. That part is standard breadth first search, or BFS. But here's the twist. Level 0, you read left to right. Level 1, you read right to left. Level 2, you go back to left to right. And you keep alternating the reading direction for every level. So it's still fundamentally a BFS problem, but with a directional flip layered on top. That flip is what makes it zigzag. So what is zigzag? Zigzag traversal is literally just a normal level order BFS, with every other level reversed. That's the entire concept. Level 0, normal order, left to right. Level 1, reverse it, right to left. Level 2, normal again, left to right. Level 3, reverse again, right to left. If you can perform a level order BFS and you know how to reverse a list, you already know how to solve this problem. The zigzag part is just one extra line of code. Our input is simply the root of a binary tree. It could be any binary tree, balanced or unbalanced, doesn't matter here. The output is a list of lists. Each inner list contains all the node values from one level of the tree in the order they should appear for that level. And those lists alternate in direction. Some will be left to right, some will be right to left, following the zigzag pattern. Let's look at the classic example to make this concrete. We have a tree that looks like this. Your zigzag output should be from left to right. The first group is 3, the second group is 20, 9, and the third group is 15, 7. Let me break down why. Level 0 contains just the root, which is 3. We read left to right, so we get 3. Level 1 contains 9 and 20. Normally, in left to right order, that would be 9, 20. But level 1 reads right to left, so we reverse it to get 20, 9. Level 2 contains 15 and 7. We're back to left to right, so we get 15, 7 in normal order. That's the entire pattern. Collect each level, reverse every other one, and you're done. If the tree has just one node, like the value 10 standing alone, then the answer is simply 10 in the array. There's only one level, and it's level 0, which reads left to right. No reversal is needed in this case, just one list containing one value. This edge case is trivial, but it's worth mentioning to make sure your code handles empty trees and single node trees correctly. Think of it like reading lines of text in a book, but every other line is printed backwards. One line reads left to right, next line reads right to left, next line goes back to normal, then backwards again. That's all we're doing with this tree traversal. It's a standard BFS, plus one Boolean flag that flips direction each level. The human intuition here is simple. Alternate your reading direction as you move down the tree, level by level. So the game plan is straightforward. Collect each level using BFS. That means processing all nodes at the current level before moving to the next level. Reverse the level if our direction flag says we should. If we're on a right to left level, flip the list. Add that level to the final result. Flip the direction flag for the next level. This is the simplest, cleanest way to solve the problem. No complex data structures were used and no recursion tricks occurred. just BFS with a toggle. All we need is a Q for BFS and a direction flag, something like left_to_right equals true. At each level, we process all the nodes currently in the queue. We collect their values into a list. If the direction flag says we're going right to left, we reverse that list. Then we append it to our result and toggle the flag for the next level. This is super lightweight, no tricks are occurring here, and this is the entire algorithm. In case you need a quick reminder of how BFS works, here's the basic structure. BFS traverses the tree level by level using a queue. A queue is a first in, first out data structure, like a line at a coffee shop. The steps here are push the root into the queue. While the queue has items, process everything currently inside it. That's one level. For each node you process, add its left and right children to the queue. Those children become the next level. Repeat until the queue is empty. This is the backbone of our Zigzag solution. If you understand BFS, you understand 90% of this problem. Let me walk through a detailed step-by-step process. First, determine the number of nodes at the current level. That's just the current size of the queue. Second, pop exactly that many nodes from the queue. This ensures you only process the current level, not the next level that's being added. Third, collect the values of those nodes into a list. Fourth, add each node's left and right children to the queue. These become the next level. Fifth, if the direction flag says we're reading right to left, reverse the list of values. Sixth, append that list to the result. Seventh, flip the direction flag for the next level. Repeat until the queue is empty. That's when you've processed every level. Here's the clean Python implementation. This is the code you'd write in an interview. The entire Zigzag logic is one Boolean flag and one .reverse method call. That's how simple this problem really is once you understand the pattern. Notice we're using a dequeue from Python's collections module. That's just an optimized queue that gives us efficient pop left and append operations. This solution is optimal. You cannot do better than this asymptotically. The time complexity is O of n, where n is the number of nodes. We visit each node exactly once during the BFS traversal. And even though we reverse some levels, the total time spent reversing across all levels is still O of n, because each node is reversed at most once. The space complexity is O of n as well. The queue holds at most one level of nodes at a time. In a balanced binary tree, the widest level has roughly n divided by 2 nodes, which is O of n. And the output list stores all n nodes. So both time and space are linear, which is the best you can do for any tree traversal problem. Watch out for these common mistakes. Forgetting to flip the direction flag. If you don't toggle left_to_right after each level, you'll end up reversing every level or no levels at all. Reversing before you've collected all the values. Make sure you build the entire level list first, then reverse if needed. Trying to push children in reverse order instead of just reversing the list. That's unnecessarily complicated and error-prone. Mishandling empty trees. Always check if root is none at the beginning. Incorrectly mixing queue logic with stack logic. Stick to pure BFS with a queue. Don't try to be clever with stacks unless you have a specific reason. If you stick to clean BFS and a simple flag, you'll avoid all of these pitfalls. There's another approach worth mentioning, which uses 2 stacks instead of 1 queue. 1 stack for left to right levels, 1 stack for right to left levels. You alternate between the stacks as you process levels. It's an interesting academic exercise and it does work, but here's the thing. It doesn't simplify anything. The BFS plus flag version is cleaner. It's more intuitive and it's more flexible. If you need to modify the traversal or add features, the BFS approach is much easier to extend. So while the 2-stack method is valid, I recommend sticking with the BFS approach unless you have a specific reason to use stacks. This problem reinforces several fundamental concepts. First, level order BFS. This is one of the most important tree traversal patterns, and you'll see it everywhere. Second, alternating logic with a simple Boolean flag. Sometimes the cleanest solution is just a toggle. Third, clean queue operations. Understanding how to use a queue correctly is essential for BFS problems. Fourth, how to transform traversal output. You don't always want raw traversal order. Sometimes you need to reverse, filter, or transform the results. Fifth, how to keep solutions readable and efficient. The best code is code that's easy to understand and debug. If you can solve this problem cleanly, other BFS variations like level order traversal, right side view, and bottom-up traversal become much easier. They all use the same fundamental BFS structure with small modifications.
And that's a wrap for day 14. If you like this video, like it down below, share it with a friend, comment, subscribe to our channel. We would love to have you and share future breakdowns.